Hello everyone. I want to talk about Hess's law today. In Hess's law, as defined, it basically says that if a reaction is carried out in a series of steps, delta H for the overall reaction will equal the sum of those individual steps. Okay? So if we take a look at the graphic here, most of the reactions we see go from A to D. Okay? That's what we see. But in reality, we realize that there are intermediate steps from A to B to C to A to B, B to C, and C to D. So with these steps, we'll call them delta H1, delta H2, and delta H3. That sum of those is equal to the sum of delta H total. Okay, so those two are equal. And when we take a look at a closer look at this, this is actually the combustion of methane at the top, CH4 plus O2 right here, and of course down here is the products. Well, what they realized is when they looked a little closer here, there was actually an intermediate step. Okay, so these two numbers here add up to this. That's all it is. Okay, what we're going to do is we have found that these intermediate steps have been recorded, have been tested, have been measured as far as the delta H goes. So all we need to do is add them up and make everything work. And by that, let's refer to this slide. So when we talk about Hess's law, or calculating reaction quantities, delta H, we have to consider these two steps. So if you're going to reverse a reaction, then you need to reverse a sign. And if the coefficients are multiplied by an integer, because if you have more fuel, then you have more reactant, then delta H will be bigger. So therefore, if the coefficients are multiplied by an integer, you must multiply delta H by the same integer, okay? And I know this is kind of strange, but when in doubt, just trial and error, okay? When in doubt, it is trial and error, okay? So if we take a look at this one, this is a nice, easy one to start off with. You'll have what I call the target equation. So it says use the above information to solve for delta H for the following equation, where carbon is equal to 1/2 O2 yields CO. Let me talk about this 1/2. This is going to pop up a little bit more. You don't have to use whole numbers all the time when balancing equations. If I want to make just 1 mole of a product, typically we see halves and quarters and stuff like that pop up. So again, typically if we're going to look at some calculations or some theory or concepts that involve producing 1 mole of a product. Well, this is 1 mole of a product. In order to do that, I need to use half of the O2. Okay, half a mole of the O2 to do that. So that's where the half comes from. So don't be confused with that just yet. And if you have questions on why that exists in class, we can talk about that. Okay, so if we take a look at this problem, I need to get this target equation here. So what I'm going to do is I'm going to recognize that I have 1 mole of carbon on the left in the reactants. Here is the only place carbon exists. It's 1 mole on the left, so I'm going to keep this equation absolutely as is. Okay, but I notice this second equation right here, I need 1 mole of CO as a product. Well, this is 1 mole, yes, of CO, but it's a reactant, so I got to flip this equation. So I'm going to just flip it right here just by doing this. And if I flip the equation, you have to flip the sign. Okay, so now that's positive. Okay, now this equation doesn't exist anymore, so scribble that out or get rid of it or write it on your paper. I'm sorry, write what I wrote here on your paper. So you keep track. Now what you do is you add the two equations together. And I'm going to switch colors so you can see this. So whatever appears on the left side and on the right side, or the reactants and product side, they cancel. If you have two things on the same side, then they add. Okay? So you'll notice C stays, so I'm going to box that in. I specifically worked with CO, so that stays. The CO2 should cancel. This one's a product, this one's a reactant, those cancel. And look at, I have 1/2 O2. Perfect. So let's rewrite the equation where C, so I drop that down there, plus, oh, I'm sorry, it doesn't cancel. This cancels out with this, giving us 1/2. I'm sorry, I screwed that up. So now I have 1/2 O2 yields CO. So without that little whoopsie that I had, I thought the 1/2 stayed. It does not. 1/2 cancels out with one of these, giving us 1/2 here. That's where that came from. We need that. Yeah, that was a huge mistake. So hopefully you followed along there. So I wrote this, this, and this all down here. The last step is to add up your energies, okay, which I didn't screw up. So if we add up the energies, you have negative 393.5 plus 283 the total delta H of the system is negative 110.5 kilojoules. Okay? That's how you do Hess's law. We'll practice more in class. I think I have one more at least. I think there's a bunch of these practice problems that we'll do, or we could do. So we'll do all these in class. And this, again, it's not that hard. So let's try this one here, okay? So again, here's the target equation here. So make everything fit that, okay? So what we have now is 2 carbons, okay? So I have 2 carbons here. So the only place carbon appears is here. But you'll notice I need to double them because I have 2 carbons on the left. Here's 1 carbon on the left. So let me double everything, 2, 2, and 2. But of course I need to multiply this by 2. So that's negative 393.5 times 2 gives me negative 787, okay? So now we have negative 787 kilojoules. Okay, so that works. Okay, now the H2. Well, again, I'm looking for isolation here, and the only place H2 appears is here. That's good. I have 1 mole. I have 1 mole in my target equation. That works. Now the C2H2 is a little bit more trouble here for us. It looks like we have to flip the equation. See, there's 1 mole of CH2 here as a reactant, but it's over here in my target equation as a product. So I do have to flip this equation. So let me flip this. And I have 2 CO2 plus H2O liquid. By the way, I would label the versions of water because they vary. You'll find out the more you do these, you have to do that. Plus 5 halves O2. That's weird. Now flip the equation, flip the sign, so that's now positive. Okay? All right, now let's see if we can cancel things. Okay, hold on. Let me get rid of this so we don't get confused. Okay? Now, let's see here. I'm going to box in what I need. So I have 2 C's. That's good. Okay? I have 1 H2 on the left. I need that. That's good. I have 1 C2H2 on the right. Yeah, there it is. So that works. Everything's good. Everything should cancel now. Okay? So I have 2. I'm going to save oxygen. That looks like a little trouble there. Look at 2 CO2s on the left, 2 CO2s on the right. Good. Now, add. Remember, if they appear on both the same side, you add them. So that's 2.5 or 2.5, which is 5 halves O2. 5 halves O2 on the left cancels out with 5 halves O2 on the right. We end up with our perfect equation, or at least the target equation. I don't know if it's perfect, but 2 C's plus an H2 yields C2H2. And now add up the energy. So you have positive 1299.6 minus 787 and minus 285.8. You end up with 226.8. Delta H for this reaction is 226.8 kilojoules. Okay? And that's Hess's law. Okay? We'll practice more of these in class. Again, there's a bunch of practice problems here, and then we'll get to enthalpies formation next. Okay? Email me with questions.